since we didn't get to do this last time. So this is what the really PowerPoints I had before. I pretty much like acted out on Wednesday. We're looking at the fatty acid catabolism. Once again, make sure you look at chapter 10 on your own, especially for the vernacular and like what the idea of saturated versus trans fats and all that kind of stuff. We talked about acetyl-CoA. In fact, no, I'm going to be really loud. I'm going to be able to hear me all over the place. Sorry. But I wanted to do that just in case Jonathan came in and just wondered why we left. So we have the citric acid cycle. Acetyl-CoA can enter into the citric acid cycle. We have, and we'll talk about this later, this in much greater detail later on, about what the ketone bodies mean and what they indicate. Because we haven't discussed that so far this semester, or so far this year. And then finally we did talk about a little bit, just briefly, how that plants utilize it as a biosynthetic precursor primarily, rather than energy. Okay, we talked about the problems, the fact with if you use fats and fatty acids, primarily the physical properties. That's one of the major problems because it's hydrophobic. We're water-based, and so therefore you have to worry about things like transport. How do you get them from the adipose tissue to where it's needed? And also the fact that it's both blessing and a curse in the sense that they are chemically inert. So they aren't real reactive, that's good. You don't have to worry about exploding, spontaneous combustion or something like that. However, at the same time, you really have to give it some energy in order to get the energy out because it's fully reduced, with the exception of the carboxylate end. But you can't. That means there's more potential chemical energy than actual reactivity. And we talked about the three sources. We have those that are in the adipocytes. And so they're huge, and we'll talk a little bit more about the morphology of the adipocytes later. We had the endogenous, those that it's biosynthesized, it's primarily in the liver, biosynthesized by your own body. And then we had the exogenous, or the diet-based. Okay, and before I go on, I told you about the pictures, and actually this I have to say one good thing about this projector here is it does a much better job looking at the colors. You see the healthy liver versus the fatty liver. Someone has some type of fatty liver disease going on. I don't often remember if this is supposed to be alcoholic or non-alcoholic fatty liver disease. Okay, but then we have the exogenous, those that are based on the diet. And I already warned you, those numbers were preceding the big push against trans fats. I cut off, but I did just have what the source was on there. Okay, that was this little cartoon. And then we went over, and this is really the part from chapter 10 of last semester, where we talked about tags or triglycerols or triglycerides, free fatty acids. You can see what happens to the shape of the fatty acid as you make it more and more unsaturated. It's kinky. Okay, and so, let's see. And on your own, you want to review what that does on the physical properties. Okay, I'm not going to go over that. We already shoot with it. Then we left off when we really started talking about this, the fact that insoluble fat in your diet, you have to make sure that you emulsify it first. Of course, you can't just absorb fat by itself. Right? And so that's primarily from the bile salts. Okay. And so this is the actual figure that we were talking about. All right. And so I do want you to know this. And we left off about halfway through. So, yeah, I do have that. Okay, good. So primarily, make it a little bit smaller. What happens here, you have a fat that you've ingested in your diet. You can do some hydrolysis of it, but it's not going to be absorbed prior to the actual entering of the intestines. And so the gallbladder is what produces the bile salts. The bile salts are used to emulsify these dietary fats. And then the lipases in particular of the small intestines are what going to help degrade them down into the individual fatty acids. Okay. Then the fatty acids actually are going to be absorbed through the intestinal mucosa, and they're going to form and be incorporated into these huge apolipoprotein complexes. Okay. And so we'll go over the different types in just a moment. Let me make sure I don't misspeak. Yes. But for example, the chylomicrons. Okay. chylomicrons then are going to go through the lymph system, ultimately to enter the bloodstream. The bloodstream is what's going to go ahead and deliver it through to the appropriate tissues. Okay. So we're going to go into much, much greater detail in chapter 21. I don't know why. Well, I mean, I do know why. The book, like as I mentioned before, they first try to break everything down with catabolism, and then they're going to start building things back up with anabolism. So that's how it's kind of separated, rather than just saying, okay, this is the fats and the lipids, this is the carbohydrates, this is so on and so forth. So if you just want to review just a couple of terms, what is APO? What does the prefix APO mean? We use it for other times. I don't know if we use it so much with lipoprotein, but we used it with APO, like APO enzyme, APO, whatever. What does that mean? This means without. And so apolipoprotein means it's without its lipid. So the complex is just waiting for the lipids to be loaded, so to speak. And then the lipoproteins vary. They vary, B-A-R-Y. They vary from very low, B-E-R-Y, density lipoproteins all the way up to very high density lipoproteins. So we have the VL, DL, the LDL, the IDL, HDL, VHDL. Right. This is just a picture of one. Then they also have marker proteins and phospholipids and stuff on their outside. But they are very, very condensed. That's not the right word. Densely packed. That's a better word. For the way that they're, since they want to exclude water on the inside. Okay. All right, this is really what I wanted to focus more time on for today, this flow chart and how the hormones, and you just start to think about what would make logical sense, and I'm just trying to memorize everything. And it's also going to start to try to try to tie together some of the things that we've been talking about so far this semester. All right, so first up we have the hormones, and it's epinephrine and glucagon that will start this process. Okay, why does it make sense? Let's just start with epinephrine. Epinephrine is also commonly called adrenaline, and what's an example of when you're going to have your epinephrine and adrenaline increase all of a sudden? Fight or flight. You're running from the bear. Remember my disclaimer, run downhill from a bear, you don't run uphill. Okay, but yes, so you're running from the bear. So what does it make sense you're going to want to mobilize stored fats? You want to free them up. Get more energy. Okay, you're going to need to run from that bear. And then we also have glucagon. You're not running from a bear with glucagon. Well, you may be running from the bear with glucagon, but what is glucagon? What is its importance? We've already talked about it a little bit already. Sometimes, you know how in art, let's see, this is art integration once again. Sometimes there are different types of paintings in arts where the object is defined by the negative space. Glucagon is that way for me personally, at least. Glucagon is kind of hard to always, for me to remember about, but if I think about its antithesis or its arch rival, which one was its arch rival? Insulin. I don't know why insulin is so much more easy for me to remember than glucagon. So then, what does insulin do when you have insulin? Yeah, it's to decrease the blood sugar. So what, with respect to energy levels, is it when energy level is high or low? When it's high, we have enough that we're going to start sorting. So glucagon being the negative space of that, or the antithesis, or the arch rival, or the bizarro Superman to it. What will glucagon be?
Circulating sugar in the blood.
It's to increase the blood sugar or increase your energy supply, so they're relatively low. So it should make sense that it will typically behave similarly here. Okay, it's going to trigger the GPCRs, or stand for G protein called the receptors, right? To activate adenylyl cyclase. This is a review. What did adenylyl cyclase do? It is an enzyme, obviously, but what does it do? It's cyclic AMP, and cyclic AMP will activate the secondary messenger. What? PKA. PKA stands for protein kinase A. Technically, it's got a really long name, which is camp-dependent protein kinase, but they've run protein kinase A. See? All right. What does PKA do? Since it's a kinase, it will. It's going to transfer phosphate groups using ATP, or GTP, but technically this one is ATP. Okay. And it does a lot. With respect to fats, here, there's a specific one that's going to phosphorylate, but there are lots and lots of substrates for pKa. That's why it has that generic name, protein, can you say, rather than being a very specific one. One of the proteins that gets phosphorylated is called perilipin A. Okay, which means peri's around in the perimeter kind of thing, like in lipids. A is A. So perilipin A, it's a surface protein. Okay, that's on the adipocytes. Technically, it's on the lipid droplets of the adipocytes, but yeah. Perilipin A, whenever it gets activated, it recruits. I like that word, recruits. It activates the hormone-sensitive lipases. Which what do lipases do? They break down the lipids. They break them down to make fatty acids. Okay. And technically, it makes sense. Perilipin A is what brings them, recruits them to the right area to break it down. Otherwise, it's not going to make any sense. Okay, so they're hydrolyzing tags, the triglycerides, the triacylglycerols, okay, into free fatty acids and glycerol. So you get two, well, technically you get 4 products. 3 of them are fatty acid derivatives. 1 is glycerol. Yes.
So this is a GPCR in adipose tissue. Where does this happen?
Yes. Yeah, with respect to this. So GPCR for adipose tissues. So that's the effect of these hormones on the adipose and the adipocytes. What in the world? Oh, can't read it. All right, which one do I do first? Okay, so we get, technically there are 4, but you get 2 classes of products. The free fatty acids, you get 3 of them, and you get the glycerol. Let's do the free fatty acids first. Where do the free fatty acids go? They've got to go into the blood. Okay, you can't stay there in the adipocyte. You know, it's kind of, you can't walk on water until you step out of the boat. And that's kind of thing. You know, it's not going to be able to be energetic, it'll be used for energy. It stays in the adipocyte. It's going to go on out. So it's going to go into the bloodstream. Obviously, it can't go just directly, loose in the bloodstream because otherwise it'd clot, it'd clump up, and so it'd be really bad. This is serum albumin. Okay, serum albumin, remember this is kind of like the taxi cab or the shuttle service for the blood. It definitely binds not only just fats, but lots of metabolites. It binds a lot of xenobiotic things. You know, it's just a shuttle service. Okay, so it binds the serum albumin. Serum albumin will cause a shock to the system. Okay? And we'll get more to that later. Where does glycerol go? What? No, you're going to want to use it. I mean, you're running from the bear. So if you're running from the bear, where do you want glycerol to go? To the cells, okay, but what would you want it to do? Think about metabolism. Pardon? Eventually, what's that metabolic pathway called? Glycolysis. All right. So that's where we come to. Okay. So remember, we got the free fatty acids. Free fatty acids right now is not floating, but it's on the shuttle system to get to the tissues. Glycerol can go into glycolysis. Now we have to start to think about how or where in glycolysis it can go. Using our handy-dandy logic from biochemistry and our known love of enzymes. Okay. So the first step, I have my sugar-free lifesavers too. That is not product endorsement for sugar-free lifesavers. So if someone from their company wants to support me in my habit so be it. Okay. First step, we have glycerol becoming glycerol 3-phosphate. Uses an ATP. So what class or classes of enzymes could this possibly be? Kinase. So if you were going to name this one, what would you name it? Glycerol kinase. All right, so we have glycerol kinase to make glycerol 3-phosphate. Glycerol 3-phosphate becomes dihydroxyacetone phosphate, or more lovingly referred to as DHAP. Okay, utilizing NAD plus to become NADH. Oh, okay, stuck one out. Okay, what class or classes of enzymes could this possibly be? It's a dehydrogenase, and we know that because what's the good giveaway? The NAD to the NADH. Okay. And so if you were going to name this one, what could you name it? It's glycerol 3-phosphate dehydrogenase.
Would you allow like an alkylase since it gets DHAP and glycerol at 3-phosphate?
That enzyme does not make it an alkylase because at this point in time it's not going to both.
Okay.
All right. So now we have DHAP becoming glyceraldehyde 3-phosphate. What are some of the possible classes of enzymes could this be? It's isomerase. What one is it? It's TPI. Well, this is technically DHAP is glycolysis. This is just that stepping glycolysis. That reminds the numbers. Yep, this is TPI, triose phosphate isomerase. This is what we've seen before. Give everybody a moment to get caught up. I really like the next cartoon because it's just a little cartoon to depict that flow chart and everything that we've seen. So way if flow charts are your way to go, yay. If they're not, maybe this will help. Yay. That's this one. Let me make it a little smaller though. This does not show you glycolysis. That portion, it only shows you from the perspective of the fatty acids. Okay, so please keep that in mind. But we can review and walk through it. So you have the hormone, whether it's glucagon or epinephrine. It binds to the GPCR. Of course, it's just the G protein. And it turns on adenylyl cyclase, which makes CAMP. CAMP activates PKA. PKA is going to activate a couple of things. One is the fact that it technically does turn on the hormone-sensitive lipase, but it also is what will phosphorylate and activate the paralipin. Paralipin A technically is what's going to recruit and move this lipase to the correct location, which is on the lipid droplets right here, which takes the tag, hydrolyzes it by the lipid. The lipase. Then the free fatty acids, of course, like I said, the glycerol goes on to glycolysis. The free fatty acids then are going to exit the adipocyte, catch the next ride on, the floating by serum albumin, and then that's going to take it throughout the system until you get to your fatty acid transporter. Okay, and the fatty acid transporter at whatever the target cell is what's going to recruit it in, and that's where we have beta oxidation that's going to occur, which we're going to talk about that later. Okay, and ultimately you're going to get carbon dioxide, but you do make ATP. Okay. All right. Any questions so far for that up to the transporter? We're now going to start talking about what happens on that end. Okay. All right, once it reaches that target, it has to ultimately get to the mitochondrion. So remember, I don't want to attempt to draw it on here, I don't want to get it out. Remember we've been making, I had suggested that you have that big picture of a cell and the mitochondria and putting the metabolic pathways and stuff. You can also add this to it because that free fatty acid It's got to get all the way into the holy of holies for faith integration, which is the mitochondrial matrix. But it just can't go on in. Okay, and that's where the faith integration stops because, you know, in the Bible, the high priest only could go once a year to first mercy throne. This one, we would die. That's true. Okay, so that's where the analogy stops. Okay, so we've got to make sure that we have a way to get into the mitochondrial matrix because that's where beta oxidation occurs. Okay. I shouldn't say that. I don't want to jump the gun here. Okay, so we have to have a transporter. I really don't like this figure. This figure came from the old book. It's really ugly. I don't remember the new book. I haven't checked the most recent edition, but in the PowerPoints that they had given, they didn't have a really good figure either. Just to review, the little figure that's up there in your right, that's just to remind you what an acyl or an acetyl group versus an acyl group would look like. A acetyl would only have a total of 2 carbons. Acyl will have more than 2. It could be 2 or more. And remember, for fatty, that's why you have to be really careful when you're naming things. Typically, if you name it acetyl whatever, you are limiting it to only 2 carbons. So, many times it's called acyl, so that's why that says acyl adenylate, because that means it could be 2, it could be 20 carbons long. So you first have to activate it. This is the overall reaction. Overall, you start off, remember, a free fatty acid ends with a carboxylate. It does take ATP. You know, it takes energy to make energy kind of thing. And you're going to ultimately get a thioester. We'd already talked about the reason why. Your sulfur is both a good nucleophile and leaving group as compared to oxygen. Or it's a better one, I should say. Oxygen is good too, but sulfur is even better. And it's a 2-step process. So the first step, I don't like the way they had this drawn, that's why one of the reasons I don't like it, is you're going to adenylate this. And so this is, instead of adding the phosphate group here, you're amylating it. If you want to think, use amp as a verb. Okay, you're going to amp it up. So you're going to give off the pyrophosphate. And the only reason, once again, is that's activating that. It's a good intermediate, because A and P is a great leaving group. And then we have acetyl-CoA come in. I'm sorry, see, I did it too. I didn't just do it out of habit. We have coenzyme A come in, and this sulfur then can be good nucleophile. It comes and smacks the carbon of the carbonyl group. You know, you make the tetranyl intermediate, you collapse the tetranyl intermediate, and you kick off the A and P. That's all that's happening right there. So there's the A and P, and we've made a thioester. So it's some type of acylated thioester. See, that's how they say acetyl-CoA. It's acyl-CoA. What class or classes of enzymes can this be? What are some of the enzymes that utilize ATP? A synthetase in kinase too, but this isn't a kinase because we're not transferring the phosphates. So this is a synthetase. What are we synthesizing? Synthesizing. What are we making? I can't see it starts to say synthetase enough. I forget what it's called. We're making an acyl-CoA. Okay. So let's put that together. If you're making acyl-CoA, you put those together, it becomes acyl-CoA synthetase. All right. But we're still not inside the Holy of Holies yet. So this is what we have. We have, let me make it smaller so you can see it. And let me draw. Just because, at least on my end, my old eyes have problems seeing it. That cytosol is really kind of tiny. So that's the cytosol. This is the IMS, or the intermembrane space. Remember, it's intermembrane. I've heard some people say intermembrane, I-N-N-E-R, but that doesn't make logical sense, because that's the inner membrane and there's not a space inside it. So it's an intermembrane space. Then we have the inner membrane, and then we have the mitochondrial matrix. I've been referring to as the Holy of Holies of the cell, at least, in that sense. So we've ultimately have to get this acyl-CoA and drop off. Well, ultimately, you're going to have to get it over here, but it just can't cross on through all the way. Okay? So it can get through that outer membrane. The outer membrane is a little bit more forgiving, I guess you could say. Whoa, did not mean to do that. That happened. So you can get through the outer membrane, but it cannot get through this inner membrane. This is where carnitine comes into play. And this is one of the reasons why carnitine can be used as a muscle, like an energy supplement sometimes. Because, if you eat decent amount of carnitine, you have, at least in theory, you could help make it more easily for beta oxidation to occur. Okay. I'm trying to give people a moment to get caught up, because there's a lot that is going on here with lots of arrows. So what happens is it's the coenzyme A part that just doesn't cross over, if you notice. So just like we've seen this kind of thing with NADH and things, remember the NADH itself doesn't cross over, so we have to use like mainly dehydrogenase to transfer the electrons from the NADHs on one side to the NADHs that's inside the mitochondria. And the same thing, or similar thing, is happening here, just not NADH. Coenzyme A, you can almost think of it as two pools, and don't ask me, I don't know how the limited pool ended up inside the mitochondrial matrix. It's beyond my pay grade. Okay, but we have a pool inside here. We have a pool that can get all the way to the inner membrane, the intermembrane space. Okay. So what we do here is we actually take the acyl group off of the coenzyme A, and we put it onto the carnitine to make acyl carnitine. Acyl carnitine can go back and forth. These are called acyl carnitine transporters. I know, really. Like, they're very descriptive. Like what they do, they transport carnitine and acylated carnitine. So then the acyl carnitine can come back over. And then one of my critiques for this is, it's kind of hard to tell, but there's a line there. This is the same enzyme. It's inside the inner, inside. It's a part of the inner membrane space. In the inner membrane, so I did it too. The inner membrane. And so it's just the reverse reaction here, to where it's going to take the acyl group off the acyl carnitine and add it to a coenzyme A that's already inside the mitochondrial matrix. So that way beta oxidation can begin. And then the carnitine can be transported back out using that same transporter. So what kind of enzyme, what class of enzymes can do this? Move the acyl group around. What class of enzymes would it be? It's a transferase. It's not a mutase or an isomerase, because mutase or isomerase would indicate that the acyl group or the coenzyme A itself is being turned into an isomer, and it's not. It's really transferring or moving the acyl group from the coenzyme A to the carnitine. And so it's a transferase. What kind of transferase is it? It's an acyl transferase, not acetyl. It's acyl, meaning that it can take more than 2 carbons or more. Okay. So we have an acyl transferase. Now, what specific acyl transferase is it? Someone said it. It's a carnitine acyl transferase. Because that's what the enzyme tells you exactly what it's saying does. It transfers an acyl group to carnitine. Okay. All right. Are there any questions?
So,
actually now followed, you can almost make like this to a movie, followed the fat from where it was being stored all the way to where it's going to be utilized for energy. So,
And beta oxidation only occurs in the mitochondrial matrix.
Right.
It cannot occur.
right. Well, the primary place is mitochondrial matrix. There are some specialty fat enzymes that are like in the ER and places like that. We'll talk about those in these sessions. But yeah, your predominant energy source is going to be mitochondrial matrix. There are things like desaturases and things like that, known for like the specialty fats. So it's a little asterisk. Any other questions? Everyone's going to be ready for the quiz on Monday. Okay. Then